Okay, so let's recap. So, so we mentioned two beta functions. So the beta function tells you when you have a theory with a given coupling, how that coupling runs as you integrate out fast modes. In other words, as you zoom out to the infrared, as you go to low energy, how does your coupling behave? And we wrote two beta functions. First for the two-dimensional ON nonlinear sigma model. Next for four-dimensional Yang-Mills theory. Both had a very important feature, which was this negative sign, this minus sign, right? Which means that if G is small but positive, right? If the coupling, either what I call G and what I call E0 here, if it's small and positive, and we integrate out, we go to 0, right? The derivative is negative, so we are kicked to 0. And so at high energy, we go to a free theory, and we have what's called asymptotic freedom. However, at low energy, on the contrary, the coupling becomes big, the theory becomes strongly coupled, and we don't have that many tools to study the theories. One tool that was very useful was large N. So how did it work? So first, based just on the beta function, we argued that if particles would acquire a mass, that mass will be non-perturbative and it will be something like this. That was purely from the analysis of the beta function. And this, when n is very large, behaves like this. You can drop the -2. And indeed, this is what we derived from large n. This was nothing but the expectation value of the Lagrange multiplier. What we saw is that at large n, because the fields are so much, you can integrate them out, and the Lagrange multiplier will be frozen to this constant value plus small fluctuations. And because the Lagrange multiplier is constant, is roughly constant, it means the fields are basically free massive fields. Now, what if you don't go exactly to large n, but you go to n equals 8? Very big. Well, then lambda fluctuates a little bit, and so the particles will have some mass, but it will not be just free particles, because lambda is also fluctuating, and so on, and you get a strongly coupled theory of 8 massive particles. When you have the massive particles, the particle has an index A that runs from 1 to n, and symmetry is restored. Right? So we start with ON symmetry, there was no special direction, and indeed you have n particles, you can rotate amongst the n particles, and there is no special direction. In the UV, however, symmetry is broken. Symmetry is broken, and you get n minus 1 massless particles. You can think you are expanding around the North Pole. The classical intuition would be that this would be the good description everywhere, because you have some symmetry. The least energetic configurations would be just the vector being pointed in the North Pole. So why don't we just break the symmetry, go to that vacuum, and then there will be massless modes corresponding to fluctuations around that symmetry breaking state. That would be the classical intuition. That classical intuition is wrong. It's wrong because it's very easy to break order. Order is favored energetically, but entropy wins always. Right? In 2 dimensions, there is always this competition between entropy and the energy, but entropy always wins in 2 dimensions if you have a continuous symmetry. So even though energetically you would like to put all the vectors up, you start putting the vectors up, then they start tilting and moving randomly far away. So you cannot preserve this phase, and indeed, this is precisely what we see. Okay. Now, let me just make a... Yeah.
When you say like large n limit, what would be n? Like what is the order of n that would be considered large?
6. 6 is large, 5 maybe. But in practice, let's try to see what we could say. We could say that n is large. We could imagine that E0 is small, but we could define a limit where E0 goes to 0, n goes to infinity, and this product is fixed. That would be a good scaling, right? So now, indeed, if you look at just the beta function at large n, and you want to ask, when n goes to infinity, what scales nicely? What is a good limit? You see that you would like n is here. Here you get 4 powers of the coupling. Here you only get 2 powers of the coupling. So you could want to do the following. you could want to multiply by n here, and here you would multiply. Let me do it in a different Blackboard. You would want to say that the derivative with respect to log of the cutoff of n times E0 square is equal to minus n, this is, now I'm doing large N, minus n E0 square over 2 pi. Okay? And so this variable, if I say that I start at some energy scale with n very big, E0 very small, and this product fixed, this is a double scaling limit, right? So this would be the natural double scaling limit. E0 would go to 0, n would go to infinity, and E0 square n is held fixed. This is what is natural, because if I start with this limit of large n and E0 small at some energy scale, and then I zoom out, I get that it preserves this limit, right? It evolves nicely with constants of order 1. We could do the same analysis for Young-Mills and ask for Young-Mills what would happen. For Young-Mills, we have that equation over there. Let me write it like this. Let's multiply by g the left-hand side and say that the derivative of g squared with respect to log lambda, let's bring it to a form more similar to what we have, is, well, if I multiply by g, it's something like minus 11 thirds. There is some 1 over 32 pi square. And then there would be a g to the 4 here. N times g to the 4. The 4 is far away for some reason. So now let's try to make the scaling nice. So how would you do it to define a quantity that would be fixed under Rg? Yeah?
Sorry, is it 32 pi squared or 8? 8.
So if I multiply by, yeah, 8, good. Thank you. So what should you define? What limit should you take? So what would be the natural limit? So we want to send n to infinity, g to 0, and what would you hold fixed to have a good limit in this equation? How would you do the same game as we did here? Here we saw this is indeed the nice quantity, right? So now here we did not do this analysis, but we can just do it at the level of the beta function. What would you do?
Keep n g squared fixed. Multiply.
Very good. So multiply by n, and then you see why I did. And so the natural limit is n to infinity, g to 0, and n times g squared, which is usually called lambda. It's a new coupling. It's called the 't Hooft coupling, would be held fixed. If we start with this limit at some energy scale, and then we flow, we stay in this limit. So this would be a good limit to take large n in non-abelian gauge theory. Which is where we go now. So what we are going to check now is that we study large n non-abelian gauge theories. And in particular, we are going to say and see that they are string theories. Okay. So large n non-abelian gauge theories are theories where your gluon, a mu, which is a function in space-time, has some indices I and j, where this I runs from 1 to n. And therefore they don't commute. And that's where the non-abelian name comes from. Right? So f mu nu would have some I and j, etc. And we are dealing, of course, with non-commuting matrices. Now, for the purpose of today and tomorrow, we are going to study the simplest non-abelian gauge theories, where here x is a point in space-time. So you typically have space-time 4 dimensions, 3 dimensions, 2 dimensions. We are going to consider space-times of 0 dimensions. Okay? So we are going to study 0-dimensional gauge theories. In other words, space-time is just a point. There's no space-time. And instead of our gauge field A mu of x, I, and j, we will have simply a matrix M, I, and j. So there is one point, space-time is one single point. And instead of integral over all possible gauge field configurations, we will have a path integral over all possible matrices M. This matrix M, let's still make it this matrix Hermitian. And so if it's an Hermitian matrix, this integration measure is nothing fancy. It is just, you just need to integrate the diagonal elements are real, right? If a matrix is Hermitian. The off-diagonal elements, one is conjugate of the other. So you just need to, for the off-diagonal, to consider I smaller than j. And then real part of Mij, imaginary part of Mij. So this is what is fancy symbol in this case. The measure means it's something very explicit. You just integrate over the elements of the matrix, and because M is Hermitian, the diagonals are real, and the off-diagonal, the upper part, is the conjugate of the lower part. So this is the integration of all the matrix elements. Then e to the minus the functional of, say, our gauge fields and matter, perhaps, will become an action for this matrix, e to the minus an action for this matrix M, where this action for the matrix M would be, first there is a coupling. Now the coupling, I'm going to put it like this, 1 over 2g squared, as in Yang-Mills theory. Let me just make a comment that I think, I'm not sure, but I think in the tutorial you are going to put a normalization n over 2 in the tutorial instead of this. Is it true? Okay, n over 2 in the tutorial. Now it looks very different. 1 over g squared and n over 2, right? It looks different. But as we are going to see, we are going to take the 2th limit soon, where this quantity is fixed. So indeed, 1 over g squared is roughly like n. So it's not so different. They have the same order, right? So this is okay. In the large n limit, these two normalizations are both very natural. They are equivalent. And then we have the kinetic term. That would be, instead of trace of f squared, it would be trace of m squared. And then we could have interactions. And interactions, there could be some general potential that depends on this matrix. This potential could be something like some sum. For example, there could be some constants Tn times m to the n. Because I put the coupling outside here, these guys are now order 1 numbers. Like for our phi to the 4 theory, if I put the coupling outside, then phi to the 4 comes with coefficient 1 or something like this. And so this could be a general potential. Yeah.
So I understand that, like, because we're in a zero-dimensional space-time, there's no curvature, but how would something like that be gauge invariant, for example?
Okay, so let's answer that. So what would be the analog of gauge invariant? So in the same way that our action before was in f mu nu, how does it transform under a gauge transformation? In an abelian gauge theory, if you do a UN rotation, how does f mu nu, this matrix, transform?
The adjoint representation.
Yeah.
So okay, with a matrix of a group element in the
Exactly. So under a gauge transformation, f mu nu at position x transforms under omega, some rotation at position x, f mu nu times the inverse at position x. And that leaves the trace invariant, right? Because you put one f, you put another f, the omega minus 1 cancels, the other outer ones also cancel because of cyclicity of the trace. So this is a symmetry indeed of the action. And similarly now, this analog of this symmetry would be the fact that I can rotate m, I can do a rotation omega m, omega minus 1, and the action is invariant. Right? So this would be a symmetry of the action. Or a redundancy, if you want, of the action. That in practice, even though it looks like all the m matters, in a sense, only the eigenvalues of m should matter. This would be the analog of the gauge theorem.
But m is analog to the gauge field, right? Gauge field does not transform like that.
No, well, the way I wrote it, m is a matrix. The fields that are matrices become just m. I don't know, a or f. You can put f here if you prefer. I don't know. This is the model. This is the action. Here is m squared. In Yang-Mills, it will be f squared. A or f, if you don't have space-time, it's hard to tell, right? Because you don't have derivatives. So who is a, who is f, whatever. This is the definition. Okay. And so we have our building blocks. So now we can define what are called these zero-dimensional gauge theories that are called matrix models. So our one matrix model, one is because there is one m. If you have m and m prime, it's 2. But there is only one m, so it's called a one matrix model. So our one matrix model, the definition is if you want to compute the expectation value of something, this is defined as the integral with the measure that we defined there of that something times e to the minus the action of m, and by normalization divided by the partition function, which would be just the integral without any. Okay. So this is the definition of our matrix model. Let me also define the expectation value, maybe with an index 0, to be the same with no potential. In other words, if you want to do perturbation theory, the potential we will treat as a perturbation, bring down, and we'll compute expectation values with this 0 here. So this is what we do. But this is basically what we need if we want to do perturbation theory. Right? The usual thing. We expand around the Gaussian point. Okay, so now let's study this model, and we want to understand the claim why this model is supposed to have anything to do with string theory. Why is this a string theory? So let's start studying these simple expectation values, and let's start with, we have here a bunch of analogs of quantum field theory. The action becomes this, the measure becomes that, the field becomes a matrix. What's the simplest thing you compute in quantum field theory when you want to study some quantum field theory?
2-point function.
2-point function, the propagator, right? So as Manu said, let's study the propagator. The simplest, the simplest quantity you could compute, which would be the expectation value in the Gaussian theory of two fields. So let one of them be Mij and the other be Mkl. Okay, so now I'm not going to do this computation because it's very simple, but let me just tell you how you would do it. You notice that trace of m square, right? Trace of m square is what? Is Mij times Mji, right? So it's a Gaussian integral, right? And in particular, it's, yeah. Okay, I'm going to help you a little bit. Trace of m square is equal to Mij Mji, which is Mii Mii. Now, because I have 4 indices, let me really write the sum 1 to n. These ones are real, the diagonal ones, because m is Hermitian. Plus, and then the other ones, which is a sum over I not equal to j of real part of Mij plus I imaginary part of Mij times the other one with Ji, which is just a complex conjugate of this, times the same thing with minus. And so this stuff is real part of Mij square minus this guy square, which is plus the imaginary part of Mij square, right? And so now you are totally ready. You have here, by the way, this guy is the same as the real part of Mii. So this full thing is the real part of Mii square. And so you really have a diagonal Gaussian expectation where you have real part square, imaginary part square. This m is real plus imaginary. This is real plus imaginary. So you just compute the Gaussian. Correct? Very simple. So what do you get? So first of all, it's the inverse of that stuff. So there is a 1 over g squared there. So the propagator will have some g squared. In your tutorial, you would have n up there. So the propagator would have 1 over n. Again, don't forget that you might need to redo some of the things we did in class with the new normalization of the tutorial. That's the g squared. And then you have real part plus imaginary part, and you have to do this stuff, and you really understand, you can easily see that you get delta function of IL, delta function of JK. That's what you get. And in pictures, you draw it like this. You say that you have a matrix with index I and j, and because the matrix has 2 indices, you write the field as having, you open up the 2 indices, and the index I, which is this, propagates and needs to be identified with index L of the other matrix, an index j of this matrix propagates and needs to be identified with k of this other matrix. And this index I is the first index of the matrix, so let's put an arrow going out. And j is the second index of the matrix, let's put an arrow going in. And then it makes, here it's nice because L now, if I follow the arrow, it has an arrow going in, but that was the prescription for the last index, and it is the last index of the matrix. And J, if I want to preserve the arrows, I need to put an arrow going out, so this is the first index of the matrix. So you see that here you might be a bit, the first time you see it, you might find it weird that first index goes to last and last goes to first. But that's precisely what the picture would like you to do if you follow the arrows, right? Or said differently, in other words, the matrices like to be contracted like last index with first, last with first, last with first. That's how we multiply matrices. So it's not so surprising that that's the connection, but this is the result of just doing the Gaussian integration with this measure. And of course, you can also, this is one way of drawing it. You can also just say I have a matrix M here that goes to a matrix M here. This would be the usual graph notation. And here what you did is you take this graph and you made it fat. Now instead of a line, it's like a ribbon. And so this is what's called a fat graph. Or sometimes it's called a ribbon graph, because it looks like a piece of ribbon that's propagating here. So, and this is the propagator. Okay, so once we know quantum field theory, first step is the propagator. What's second step? To do perturbation theory. What do we do with the propagator? Weak theorem. So now we just now we can compute the expectation value of this potential by bringing down the potential and then just doing weak contraction. Right? So now let's go on. Step number 1 was propagator, and step number 2 is expectation value of interactions by weak contractions. Right? So 2 is now we do interactions by weak theorem. Right? So all we need to do is compute expectation value of some quantities now that we compute in the Gaussian matrix model, and we do it by just using weak theorem that tells us contracting in all possible pairs. So let's consider an example. Suppose from the potential you bring down, so because you bring down from the potential, it's natural to put this 1 over 2g squared downstairs because it was there. And then, for example, you bring down trace of m to the 4. So this would be, in quantum field theory, like expectation value of phi to the 4. What do? You draw all possible contractions between the 4 fields, right? So let's do this computation. So this is 1 over 2g squared. Expectation value of, now let's write the trace, mij, mjk, mkl, mli in the Gaussian theory. Correct? Now you have 4 fields, and all you have to do is take this guy, the first one, and contract it with this, this, or this. Right? Do all possible with contraction. There are 3 terms, right? Because the first guy can marry with the second, the third, or the fourth, right? And then the other 2 are left, and they have to be paired. And so there are 3 terms. Let me maybe put a bracket here so that I don't carry this 1 over 2g squared. And so the first one is m, let's write them all, mij, mjk, followed by mkl, mli, plus the next one would be the first marries with the third one, Mij, Mkl. Then the other two that are free, Mjk, Mli. And the last one, the first one, Mij, with the last one, Mli. And then second and third, Mjk, Mkl. All these expectation values with 0, of course.
That's supposed to be a MKL in the second time.
There is R there instead of M. The second term.
Okay, thank you. I don't know why I did that. Mij. Okay. And so now we are going to do this we are doing it in all detail. It's a bit, but it's the only time we'll do it in detail, because now we are going to find soon we are going to find a graphical way of doing this much faster. But let's continue and do it in all detail. Now this propagator, we worked it out up there. So let's really work it out. So let me continue here, equal. Okay, let me remove this 2 here. Remove this 2. I don't care about this. Now, each propagator comes with a g square. So now 1 over g square, there is 2 propagators. So in total, there will be g square in front instead of 1 over g square because of the 2 propagators. Each propagator with its own g square. And now we just write the Kronecker deltas. First Kronecker delta there is delta I with last, first with last, ik. And now delta jj. You agree? First propagator. Again, first index with last index, always. And then, let me put some parentheses to remind you that it comes from the first term. The second one, mki delta ll, plus, let's go on, delta il delta jk, delta ji delta kl, plus delta ii delta jl delta jl delta kk. Right? Always first with last, last with first. And now, what does this evaluate to? So let's just see. So j with j, I sum over j, this gives me n. L with L, I sum over L, this gives me n. Delta ik times delta ki gives me delta ii, I sum over I get n. In total, the first term gives me n cubed. You agree? And so we get equal to g square, parentheses, n cubed for the first term. Second term, someone tell me, what do you get from the second term? Just do it in your head. Whenever you have 2 deltas, you contract the indices, you get 1 delta, you do it. N, right? It's clear? Can everyone see? You just swallow all the indices. At the end, you get a single delta of whichever letter you start with, ii, and that gives n. And the last one. And the last one, n cube again, because there are 2 deltas that I've repeated, and it's the same as the first one, plus n cube. Okay. Now, let's see graphically what we just did. Let's draw these diagrams corresponding to these contractions. Okay. So now we repeat the same graphically. So we have the expectation value of 1 over g squared trace m to the 4. And this would be the expectation value of 1 over g squared, and then trace of m, I write like this. If this is m with the two indices of m, right? Then I multiply by a matrix, which means that if this is I and j, the next matrix has index j and k, and so I just draw it like this. So this would be a product of two matrices, this matrix times this matrix. Right? This tells me that this index j is the same here. This was out, this was in, and now this is out. So you see this notation, you follow the arrow, and it just tells you that mij, mjk, j is the last index first, and then it's the first index. And then you continue and you multiply by the next matrix, where the index k is here, and then there is L, and then you multiply by the last one, where you have L and I. So this is how you draw trace of m to the 4. You just write like this. This is just representing the product of the 4 matrices, keeping track of how the index goes.
Pedro?
Yeah.
I was copying and I didn't see. Can you just repeat this?
Yeah, so I just say, if you draw this matrix, the first one, ij, this is the matrix jk, and what should you do? The j is the same, so you should just connect the index j. So this part here is mij, mjk. Right? In the sense that you keep track of the indices. This line represents the propagator for m. This will be the whatever will be the propagator for the next m. But this index is the same, needs to be the same. So I connect them like this. Right? So this would be the analog in the usual graph notation to just saying that phi to the 4 is just this. Right? But here we make it fat, and now we can follow the indices. Right? So if it was not fat, it would be a pain to see what exactly we are doing. But now that it's fat, it's very easy to just follow the index where the index is. And now we have our fat vertex, and we connect it with fat propagators. Right? So now we just connect with the propagator. So how do we connect here? The first option is this guy connects with this one, and this one connects with this one, right? When we connect here, right? There are this option plus this with this, and this with this, plus this with this, and this with this. Right? Just the usual weak contractions. Right? Now we are going to do the same, but let's do it here carefully with our fat graphs. So the first one is, as I said, you contract this one with this one, and this one with this one. And then this one with this one, and this one with this one. This is one possibility. Right? You propagate from here to here and from here to here. The other one is the first matrix connects with the third one. So let's draw that one plus. So let's draw that this connects to here and this connects to here. That's the first connecting to the third. And then the second connects to the last one. So I have to draw like this. It passes below, right? And then it goes here. And it goes here. That's the second option. And the last option is the first connects with the last one. So it does directly this. And then the second connects to the third one. Correct? And now you just see that here, the index here, it's the same index, right? It goes around. So here you have a loop, a phase where this index runs, and it can take any value here. And so each time you have a loop of index, you get a factor of n. So here you have a loop, and you get n, because this loop can take any of n values. And how many loops you have? You have a loop here, you have a loop here, and you have a loop for the outer line. Right? And so you get 3 faces or 3 loops, and therefore so we get 3 loops, or we say it sometimes 3 faces, and therefore n cubed. You can call it faces. You can imagine you put a bit of glass here, and you need 1 piece of glass, 1 piece of glass, and 1 piece of glass for the outside.
Could having a loop gives n? How do we see that?
So this just means that you connect, and this can take any value. It can take value 1, 2, 3, 4. So if you sum over all the possible values, you get n.
It's just like this delta.
It's just the delta I. This is delta I, right? You have I here, and this is delta I. But now graphically, it just becomes a loop. What about here? Let's see how many loops we have. Let's follow the lines. So if I follow the line, if I start here, I go here, I go here, I go here, I continue here, I'm here, 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 and I came back. Right? So all in all, a single loop. So this as a single loop or face, and therefore this diagram gives n to the 1. And this one, again, 3 faces, so n cubed. And so we see right away that graphically these terms have this simple explanation. Okay. Now let's continue. So we conclude that we get twice this diagram, right? The first and third are the same type of diagram topologically. Right? And this diagram here is what we call is a diagram that I can draw on a sphere. I can put a sphere, and I just draw it here on the face on my sphere, on the plane. Okay. This is just a sphere. And because I can draw it on the plane or on the sphere, this diagram here, this diagram is called a planar diagram. It's also, we can also say it's a graph of genus 0. The graph I can put on this sphere which has no gene. Now the next graph plus, then I get the other graph, this one where I connect like this, and then I need to go around. And this diagram, you see, I cannot draw on the plane without lifting the chalk. Right? I cannot draw on the blackboard without lifting the chalk. It cannot be put on the plane. This diagram cannot be drawn on a sphere without or on the plane. Now you can, however, draw it on a donut. So if you have a donut, which is a genus 1 surface, so now this is not a sphere, this is a genus 1 surface. Now you can draw this graph here. You just start drawing the quartic interaction here. Okay. And you want to connect these points without crossing these lines, without going over. And you want, so this, you connect with this, this, you connect with this. Right? But now You can indeed connect them without going below by just going around and connecting like this. And this diagram is therefore called, whereas this is a planar diagram, this is a non-planar diagram. In this particular case, is a genus 1 diagram, meaning that it's a diagram that can be drawn on a surface of genus 1. Another way of drawing this same picture is thinking that a donut is just a square with identifications, right? A cylinder, you identify this with this, right? And then to make it into a donut, you identify this and this, right? And now this fancy 3D picture is just this trivial picture where I just draw it like this. This makes it obvious that I don't need to lift the pen, right? And if I identify now things, I get precisely that picture. So what we are seeing here is that we are getting that planar diagrams, at least in this simple example, when n is large, they give bigger results. That is n cubed versus n. More precisely, let's summarize here what we found. Now with all factors of g squared, 1 over g squared trace of m to the 4 expectation value was equal. Now let's write like this. Let's say, okay, let me write first. It was g squared n cubed with a 2 plus g squared n. That was the result. But let me rewrite this. Knowing that the nice Tooth coupling is what we wrote up there, let me write it as saying that this is n squared times 2 g squared n plus g squared n. And this quantity here, g squared n, is what we define as the Tooth coupling, lambda. This quantity here is therefore also lambda. And therefore, if this quantity, lambda, the Tooth coupling, is held finite, then we get n squared for the planar diagram and n to the 0 to the non-planar diagram. And so these diagrams, this here, they are dominant at large n. Now, let's work out one more, yeah, I have time. Let's work out one more example. And after working out this example, we will prove a general theorem. Let's work out another example. Let's suppose now I have the cubic coupling. We did the quartic coupling, let's do the cubic coupling. Okay, so let's do that. Expectation value, 1 over g squared trace of m cubed. What will be this expectation value?
Should be 0.
0. I have 3. Okay, so this example is done. So maybe let's do one more. If we have one cubic, it's 0. What do I need if I want cubic vertex? 4 I did already. So I want cubic.
6.
So then I need 2 of them. I need to bring down from the exponent 2 of them. So that's okay. Now we want to do this example. Okay, so let's work it out. So now it's very easy. We do it graphically. So it's 1 over g to the 4 times the expectation value of the first one, which is just now some cubic, and then the second one, another cubic I. And then all we have to do is we contract. Contract these propagators like this. Right? So there are a bunch of options. There is. So first of all, how many propagators there will be in total?
3.
3 propagators, right? I need to connect, right? I need 3 propagators, for example. And connect like this, and like this. 3 propagators. And therefore, this 1 over g to the 4, each propagator as g squared, will become, like before, a g squared upstairs. Right? Each propagator has g squared. And then, let's draw the graphs that we have. So one possibility is what I drew here. So let's draw it. So one possibility is this goes here, this goes here, this goes here, this goes here. This is one possibility of contracting. Let's work out one more, or the other ones. What else could I do?
They come to inside to itself and one.
Very good. As Ami said, you contract 2 of them within the same operator, then they contract the next one. Right? That's another possibility. Last one. There's one more. Notice that if they self-contract, it's the only option, right?
Yeah.
Because as soon as they self-contract, there's only one option. So it means they don't self-contract. So if they don't self-contract, it means that, okay, there is one propagator between them. So I can draw the beginning. Now what can I do?
Cross it. This one.
Right. So instead of connecting like this in the friendly way, I connect in the non-planar way. Right? So I connect this one with this one. And now the other one is not happy because it cannot connect. Okay, it's life. And you need to do this. And then like this. All right? What symmetry factors do we have? What factors do we have? How many terms are there for each of them?
The middle one is 3.
Sorry?
The middle one is 3. Right?
Let's see. The middle one, okay, you can, okay. The middle one is 3. What was the argument? How was your counting?
Because we have one that, like there is, okay.
If I chose that out of, if you look at one diagram, out of 3, you have to choose 2 branches. So 3 choose 2 is 3, and then everything gets fixed automatically. Because you choose one and connect. Choose in one diagram, choose any 2 and connect them. Everything else is already fixed.
So you say in one diagram, choose 2 to connect. So there are 3 options, right?
3 options in there.
And in the other diagram?
Because in the other diagram, okay, then you could have
I
3.
think one of them should be 2, one of them should be 1. Right? Because in general we have 6 options.
You choose 2 into 3, maybe 9 it should be. 3 square.
Oh, 9. Someone else, Manu says. Who is right? Manu or Hami? What do you think? So again, you have to just do weak contractions. So there are many ways of thinking. Let's go with what they said. So we decide first, we take the first operator, and we choose who is not going to be contracted, or we choose who is going to be contracted. Same thing. There are 3 options. We take the second operator, and we choose who is not going to be contracted. There are 3 options. 3 times 3 is 9. Yeah, correct is 9. What about here? Here, everyone here needs to connect to everyone here, right? How do we think? So the first guy
Has 3 choices.
has to connect somewhere there, and it has 3 choices. Right? And that's it. Once that's done, the other ones you just follow clockwise. Right? 3. The last one. 3 again. You just say who connects. That's 3 options. And then the other ones are fixed by topology. 3. Let's do a check. 3 plus 9 plus 3. If you add them up, 3 plus 9 plus 3 is 15.
Contractions for
Sorry? And 15 is 5 double factorial, right? What is this 5 double factorial? It would be the number of weak contractions if you add just 6 fields and you don't care about them and you just have 6 fields, right? And so you say the first one can choose any of 5 options, then the next one can choose 3 options, and the next one can choose 1 option. And so whenever you have n fields, you would get always n minus 1 double factorial total number of diagrams, and that's okay. That's what we are getting. Okay, and now let's see what this gives us from loops. How many loops we have? Here we have 1 loop here, 1 loop here, 1 loop outside. This diagram gives n cubed. What about this?
n cube again.
N cube as well. What about that? Follow the loop.
This is just one loop.
It's just 1 loop. N. And same story. This diagram can be drawn on the plane. This diagram can be drawn on the plane. This diagram can be drawn on genus 1 surface. So again, these ones are planar. And this guy is genus 1. And what we get in total, just to work it out, is, if I write, there are these diagrams, 9 plus 3 is 12. Let me write this 12 times g square n times n cubed times n squared plus, and then 3 times g square n as before. So 12 lambda n square plus 3 lambda. So we see that the planar graphs not only are dominant, but they come with the same n square here. Right? They are dominant over the non-planar, but more than that, it looks like we are getting, from this very simple example, we are seeing some pattern. And the pattern is that we get n squared times some function of the 't Hooft coupling plus n to the 0 times some other function of the 't Hooft coupling plus dot dot dot, where this would be planar and these guys would be genus 1. So normally it would be a good point to stop and start the next lecture by proving this statement. I wonder if I should go 5 minutes over time and prove it now for the purpose of the tutorial, or you think it's okay to stop here?
What are you going to prove?
To show that these diagrams, to do this Euler characteristic stuff and to show
Find it out themselves.
in the tutorial. Okay, so very good. So we see this pattern. And so we would like now to establish this in full generality, which you are going to do in the tutorial. And then I'll start tomorrow by recalling how that goes. And indeed, the conclusion is precisely that. But just to conclude, let me just say one thing, that what we are seeing is that the diagrams like to organize themselves by topologies. Genus 0 are the most important ones, then genus 1, then genus 2, then genus 3, etc. But that's what string theory is. String theory is defined as a sum over topologies. You have strings interacting, then strings can split and join again, and that's subleading. and then strings can join and split many times, and that's more subleading, etc. And so the kind of diagrams that we are getting are diagrams that like to be split into genus 0 surfaces, genus 1 surfaces, genus 2 surfaces, etc., exactly like string theory. And because you sum over all possible diagrams on these surfaces, it's like you are discretizing these surfaces. So summing over all possible diagrams that you can draw on the sphere is like doing a triangulation of all possible spheres. And then summing over all diagrams on the donut is like summing over all possible genus 1 surfaces. And so on and so forth. And so that's how we will see that indeed the summation over these graphs you can interpret as a genus expansion of a string theory. And that's why large N gauge theories are string theories. But that's what we are going to finish concluding tomorrow. Okay.